Hello, everyone. We'll be just starting in a few minutes, so take the time now to sit back, make yourselves comfortable, grab a glass of water, and get your pens and pencils ready, as we'll be doing some fun questions today on waves. Just gonna get set up, and I'll be right with you. Okay. Wow.
Sure.
Yes.
Yeah, I think I have a question about because I'm not sure what an equation means. Um,
All right. Let's have a look. Which equation in question?
there's the equation y equals f and then x minus vt.
Okay.
Uh,
Right.
I think I want and like what's the difference between that equation and the equation of y xt equals to f xt?
Oh, okay, so let me write that down so we're all here in the same word. So we're kind of comparing, we're looking at the vertical position of a wave and the way that we can talk about the wave function. Okay, so the difference really is that this form here is, where's my highlight button? Okay, this form here of the wave function is a lot more specific as to what the function looks like. This form basically declares that both position and time are sort of influenced by each other directly. Like, this is just saying that the function has position and time, and this is also saying that, but more specifically, that there is a direct interaction between position and time. That there's that these two are part of the same input. So it doesn't really mean much conceptually. It's just sort of giving a bit more detail as to what the function may look like, because with this form here, this could be anything where you have like an x and a t, or this is so ambiguous in the definition that heck, you could have I don't even know e to the power of x plus I don't know arc cos t. But by stating that the wave formula in this form, there's an understanding that since you're describing a moving wave, then the position and time do have an effect on each other because the position of the pulses move over time. So this kind of it really establishes that there's a interaction right away between position and time. So with this already specified, then the wave function, right, whatever it may be, its input always has x and t, I mean, put together, or or it could be anything like x minus bt to the power of 5.
Okay, thank you.
In others. Okay, well, the time is 10:03, so we'll jump right into the tutorial. First of all, good morning, everyone. How are we doing? We doing good. It's Wednesday, halfway through the weekend. I believe colloquially Wednesdays are called hump days because they're the middle of the week, so you're getting over that hump. Personally, I don't like that word. It makes me think about camel. Nonetheless, let's jump into the tutorial, which, by the way, the tutorial slides, I put them up on Omnivox if you want to follow along that way. The only thing about the slides is that some of them have GIFs, sometimes pronounced GIFs. I don't think there's an official pronunciation, correct me if I'm wrong. Especially for like section 16.1 and 16.2, there's a lot of GIFs on the slides, so you get to see them in the recordings and in the PowerPoint version of the lights I put up. But if you don't know the PDF, you won't see the GIFs. And I do recommend, seeing them or even like following some of the YouTube links I put up, because we're going to be talking about waves for a few chapters, and the textbook won't really sell you on what waves are doing, because the textbook is just showing you images of a wave that's supposed to be moving, right? So it's a lot more easier to learn if you can understand the waves, see them in motion, because that's actually what they're doing, and the textbook will really show you that kind of motion. And for this tutorial, though, I really wanted to go with the early parts of the chapter where you introduce the most basic wave formula, the sinusoidal wave, and just jumping into that here. I do have to keep an eye on the time, though, because we do get kicked out at 11 p.m. sharp, so I'm supposed to keep you here till 10:50. Right, so the sinusoidal wave function essentially describes a bunch of pulses traveling along a horizontal axis. And again, because this is not a movie, you can't see it move, but the idea is that these pulses, like waves in the ocean, are moving to the right. And in the graph here, we see the starting frame, t equals 0. You take a picture of it, you get the dashed curve, and then as time progresses, the waves move to the right. So the formula to describe this entire wave is a mouthful, right? Because you have to talk about whether or not where the pulses are
and also you're specifying a particular position on the wave. And because of that, then there's essentially two variables to this, right? There's the x variable that kind of specifies a position. So, you know, if you pick a point here, that's x equals 1.2. So if you lock that down, then what the function becomes then, it just becomes a function of time, and that will just tell you how this particular point is moving up and down as the pulses pass through it. Conversely, though, right, if you lock down time like they do here in the dashed curve, if they say, well, let t equals 0, then x is your free variable. So what you get is you get this dashed line, this graph of what the whole wave, what the whole medium looks like at that point in time. Then finally, right, there's like a final term here, the phase shift, the phi, that basically just accounts for initial conditions. So if phi is 0, then that's going to make your wave start off basically at the origin. You'll get sine of 0, which is 0. So whatever phi is, that lets you adjust where the wave starts initially. And you'll also note that the wave function is kind of modified by the amplitude term here, which is determines how tall the wave gets. And then if you look inside, there's the wave number, and this essentially is there to account for the wavelength, because the wave number k is actually sort of like the angular version of the wavelength. And you'll note though that it's not 2 pi lambda, it's 2 pi over the wavelength. And the reason that is because when you have a function times a constant, if you had the function like this, then having a bigger value will actually compress the function. So multiplying x by a constant, it actually does a horizontal compression on the graph. And we know that a wave with a bigger wavelength, right, is like more stretched out. So then what we're actually looking to describe is the fact that the wavelength does a horizontal stretch. So as the wavelength gets bigger, right, we get a horizontal stretch. And that's why the term here, kx, right, that's the same as 2 pi x over lambda. Having x over lambda means that lambda is acting as a horizontal stretch the bigger it gets. And the reason why there's a 2 pi here, well, that has to do with the fact that we're using a sine function in radians. So x over pi, x over lambda, I mean, is not in radians. And then the 2 pi is there to make it radians. But rather than writing 2 pi lambda every time, we just write k, which is again the wave number. It's a similar idea with the middle term here, omega t. This term again is your angular wave frequency, which accounts for how fast, how many pulses are passing through any given point of the wave, right? That's related to, again, the linear frequency. In the same way that the wave number k is kind of like a radiance version of lambda, omega is also like a radiance version of the linear frequency of a wave, which is 2 pi f. So even though there's like 3 different terms, each one accounts for something different. The kx term, again, is related to the wavelength. The omega t is related to frequency. And the phi here is just for initial conditions. But another very important thing that we learned in chapter 16.2 was that there's a trade-off between wavelength and frequency of your wave. As the distance between the pulses stretches out, then it takes longer for any number of pulses to pass a single point, right? The other way around is that, like, if the wavelength is very short, then the pulses are passing through at a faster rate. And the speed at which the whole wave moves, the whole series of pulses propagates to the right is actually a property of the medium. So that's always going to be constant if the medium remains the same. And that is also equal to the product of the frequency of the waves times their wavelength. So very important. Now, I said that a property of the medium, right? Then basically the what's physically happening to the medium, or what physically describes the medium, gives us an idea of what the wave speed would be. But of course, a medium where waves can happen could be water, could be rope, string, slinky. So there isn't quite a universal way to, account for all the properties of any medium that determines the speed of a wave passing through it. But we did talk about the waves going through a tense string, like a string on a guitar, or like a power line. There's some tension. So we talked about the fact that if you actually know how tense a spring is, and sorry, the string, if you know how tense a string is and you know how dense it is, you can actually figure out the speed of any wave that's sent through it. We found out that for any string, the speed is determined by how tense the string is divided by the mass density, and then there's a square root there. And right, we said that like, okay, right, like the tense of the string is, it's kind of like a spring being really stiff. A stiff spring has a stronger storing force, and as such, its frequency of oscillations is a lot faster, it's a lot stronger. And it's the same thing with a tense string. A tense string is a lot more powerful, and thus it really wants to shake up the particles and has an easy time sending the pulse through. But then the speed of the wave decreases as the mass density increases, because if a string is more dense, then it's more inert. It's harder to get the particles moving, and the wave, the pulse that's moving through the string, has to shake off the particles to propagate. And if there's more, if it's heavier, then it takes longer, and so it would be slower in a dense string. So all this is useful for all kinds of waves, not just transverse ones. The sinusoidal wave function does describe a transverse wave, but the wave speed formula here is true for all waves. And there's a formula that will be coming back to time and time again. Anyways, I thought we could put that to the test. Just gonna go on to the next slide here. Okay. Yeah, this one's for the class. I wanted to ask you. We have a light source, and we know its wavelength. It's about 5 nanometers, and actually it's 50 nanometers. And we know that the speed of light is essentially 30 million meters per second, 300 million meters per second. So with this information, we're asked to find, okay, what's the frequency of the light wave given that we know its wavelength and its speed? So I'll let you try that question. I'll give you maybe like a minute to figure it out. So again, remember, even though the light is a electromagnetic wave, there is something about it that is true for all waves, mechanical or not. Okay. D, you got it right. After all, even for light itself, the relationship between frequency and wavelength is always inversely proportional. The speed of light is equal to its wavelength and its frequency. So if you know two things, you can find the third, in this case, the frequency, the speed divided by lambda, and as such, have oh, by the way, if this were like a multiple choice on like a test, you wouldn't even have to pull out your calculator. Note the multiplicants on the numerator and the denominator, right? You have 3/5. You know that 3/5 is 0.6. So whatever your answer is, there's a 6 at the front, and the only option from all of these A, B through E that has a 6 is D. So right off the bat, you know the answer must be D, and you don't even have to use your calculator. You move on to the next question. All right, one more for the class. You know the speed of a sound wave is, it's obscuring the thing. It's 1500 meters per second. You know its frequency. What's its wavelength? Okay, I'll give you 5 more seconds. Well, if you pick C, you got it right. Basically, we know the relationship one more time between frequency and wavelength. As such, we can find the wavelength by doing some quick algebra. And again, you don't even have to pull out your calculator here, because what you have is 1500 divided by 10 kilohertz. And you know that whatever your answer is, there's going to be like a 15 or a 1.5 in front. So the only option with that is C. So not too bad. So again, this wave formula is great. It works for any wave in any medium. Okay, this question, I saw it in a homework once a long time ago. I always thought it was an interesting question. So earthquakes emit both what's called secondary and primary waves. So essentially, seismoscope will pick up these waves produced by the shifts in the tectonic plates, and the first bunch of waves that arrive are called the primary waves, and then later some after waves happen called the secondary waves, the S waves. And the P waves show up first, and then the S waves. So the question is, though, if you detect both and you know the time delay between them, can you figure out how far away the earthquake is? And the answer is yes, actually. And we just need to sort of think about the waves as the same way that we think about, moving objects in kinematics, because that's essentially what the wave is, right? But it's not a car that's moving at 900 meters per second, but it's still something that is moving. It's not matter at this time, it's energy, but we can still talk about it with kinematics. But before I even talk about kinematics, what I'm going to do for this question is what I always like doing for all the questions, which is to write down all the numbers I know. I don't like having to review the question every time we figure out a number. So I'm told some speeds, I'm told something about the time between them. We told that P waves are received 1 minute before the S wave. Nice. So writing down the information, we know that the primary wave speed is 900 meters per second. I like to use magnitudes here of 10. And we also know the secondary speed. You can also write down, like this. And again, we were told that the P waves arrive 1 minute earlier. So we need to write that in math, right? That's going to be useful for us. So however long the P wave takes to show up, that's going to be 1 second less than the S wave. Or if you think about it this way, however long the S wave takes to show up is the time the T wave takes plus a minute. Okay, but the question's asking though, the question just wants to know how far away is the earthquake center? Well, that's basically asking, all right, what's the distance to the center? Well, we know how fast they're going. We know that one is showing up 60 seconds earlier. Because they both come from the same place, they must both travel the same distance. In other words, the displacement of the primary wave must equal the displacement of the secondary wave. And you can recall then that the displacement is determined by how fast you're going and for how long you've been traveling. So we can write that as the speed of the primary wave and the time of the secondary of the primary must be equal to however long the however fast the secondary wave is times however long it's been moving for. So their displacement is also, right, whatever the displacement is, must be the distance from the center. We don't really know, we know how fast they are, we know the speeds, we don't know the time, but we do know the relationship between the times. So we might be able to do like a equation with an unknown and then figure out the time it takes for any of the waves to get to our seismograph. Because we were gonna take advantage of this formula here. Can plug in the relationship between the time. So if we do that, we end up with, I'm not gonna plug in the numbers yet. I like to do as much algebra as I can before plugging in numbers, but we can say that, okay, the time for the S wave is just 60 seconds more than the P wave. And we're gonna do some quick algebra. Again, we know the speeds. We don't know the time yet, but we can solve for that. And with a bit of algebra, you should get that the time is 60 times the speed of the S wave divided by the difference between the speeds. And at this point, everything on the right side is a number, right? You can plug this into your calculator and you should get around the time being 75 seconds. So that means that the P wave gets to you in 1 minute and 15 seconds. So if that's how long it takes to get here from the center, then how far did it travel? Well, now that you know that, right, you can figure out that, you can figure that out by just doing the speed times the time. And that's going to be 9,000 times 75, which should get you around 675 kilometers. So nothing to worry about in your area. The earthquake is pretty far. Okay. Do we have any questions so far about the stuff we've been looking at? If you do, let me know. Okay. So we're in deep water here, and we can actually find out how fast waves travel in the deep water if we know the distance between the crests of the waves. And we're asked to find the period. Well, really what this question is asking us, to find the period, but my intuition is that we've been looking at this wave formula for a while, and it's always true that the frequency is a reciprocal of the period. So we could just write the wave formula in terms of the period. In that case, then we'd see that the period, we know lambda, we know the wave speed, then we can just find out the period right away. So for that, then we could, we just need to find the wave speed. We were told the wave speed though, so we just gonna go figure that out, where it's gonna be the square root of the gravitational constant, how long the waves are, and 2 pi. So additional constants around 9.8. The wave speed was 100 meters. So at this point, again, plug in your calculators. I'm gonna say the answer should be roughly 12 meters per second. So now we know how fast the speed, the wave's going, we know how long it is, we can find out its period, lambda divided by the speed. This should be roughly 8 seconds. And of course, know the inverse relationship, know the direct relationship between period here and wavelength. The longer the wavelength, the longer the period. Makes sense. Okay. Oh, bit of a tension question. Okay, so those transmission cables you sometimes see along the highway? Well, the other one is 100 meters long and it's between 2 towers. We know how dense the cables is. We know how tense they are. Probably wouldn't touch them if I were you. I think they're coated in rubbers that won't electrify you, but still. So the question is, well, what's the speed of the transverse wave on the cable given what we know about it? So I'll give you like a minute to see if you can puzzle this one out. You'll excuse me, I'm just going to get some water real quick. Okay. So, for all of you who circled B, you got it right. Okay, so basically, knowing that it's a tense string with some linear mass density, we can figure out the speed of the transverse wave by the relationship between the tension and the mass density. Note that you're told how long the cable is. That doesn't come into effect in this question, but I'll explain why it might be useful in another case. But first, if we just plug in what we know the tension and the mass density, so we go right ahead, plugging it in, 2.01 kilograms per meter. By the way, it's always good to check that the units work out, and because you're dividing newtons by kilograms, that takes care of the, right, like a newton is, a kilogram in units times meters per second squared. So if you look at the units here, the way they cancel out is you do end up getting meters per second, which is pretty neat. So you're never sure, if you're plugging in, it makes sense. Just look at all the units. Nonetheless, this should get you about 122 meters per second, which is pretty fast. Now, what I was saying earlier about the distance here, how long the cable is, some questions might not tell you the linear mass density. They might just tell you that the cable weighs, it weighs like, I don't know, 2010 kilograms, the whole cable. So then it'd be up to you to be like, okay, this is like the whole weight of the cable, and assuming it's uniformly distributed, we can find its mass density by just taking, how heavy it is, sort of how much mass it has by how much there is, right? The length. So that would be like 2010 kilograms divided by 100 meters. And right, you'd get 20.1 kilograms per meter as your mass density. So sometimes the distance might be important. Okay, so Jane asks, could you make the square root of t over m equal to the previous equation when solving for speed? You mean the square root of the tension over mu?
Yes, that one.
Okay. By the previous equation, were you referring to the wave speed one, the lambda f?
Sorry, the lambda f. I was thinking about f. Yeah, lambda f is equal to v. So you could make lambda f equal to square root over of t over m, right? Like you could give us a question like that.
Oh,
right?
yeah,
Like,
like say
it's
relating
possible
that,
though, right?
so you could have this relationship.
Exactly. Like, let's say you want us to solve for t, but you don't give us v. Like, you give us lambda, you give us m and f, then we can solve for t, right?
Yeah, you could do that because lambda f always applies. Yes,
Okay. All right. Thank you.
no worries. The only thing though, if I give you a question like that, I'd probably be really careful to distinguish something, because the t here on the right side is for tension, and unfortunately you can write the frequency in terms of period, right? You could write lambda over t is equal to t over mu, except that the t on the left is period, the t on the right is tension. So if it came
Wait,
to that, sorry?
isn't it distinguished by like a lowercase t though? Like, because if you tell us something like this, or if we see the variable, like, how will we necessarily know? Like, you'll be really explicit with it, will you, on a test?
Yeah, no, don't worry. I would never. Gee, that'd be like a. Yeah, no, will never be ambiguous. And also, right, tension is a force, so that's in newtons, and period will be in seconds, so that's also the big giveaway.
Okay.
The textbook, if you have like the survey, they have like a little comment saying, when they introduce the t over mu formula, they have a comment saying, don't get it confused for period. Unfortunately, there's not enough letters in the alphabet, which is silly to me because we use like the entire Greek alphabet in physics, so we could have, picked some other letter.
Probably, yeah. I could see how that's like confusing for people though. Because
Yeah,
like I've seen, like, when I look at different problems and I see like the variable t, like I could get it mixed up, you know what I'm saying? But it's like nothing we can do. I mean, it is what it is.
right. Yeah, it just comes to checking the units. I think a good compromise would have been to, rather than saying tension as t, we could have written it as f underscore t.
Okay.
Capital F.
All right.
Yeah, this will come also. This will be when it's letter row also gets reused. But anyhow, yeah, that's all I wanted to say about this. I do want to I do want to talk about the wave function once, so maybe we'll have time.
Sure.
Yes.
Does wavelength and frequency have an effect on velocity or no?
Nope. Velocity
then-
is a property of the medium.
Wait, I'm like the v in the equation of v equals f lambda is the median, not the velocity.
Well, no. The v in that formula is speed of the wave.
Is the speed of the wave?
Yeah.
So then how doesn't frequency and wavelength affect the velocity if they're both in, if they're in like the same equation?
It's the other way around, right? Because the speed is constant. Once you know what medium you're in, you know that no matter the frequency or the wavelength of any wave in that medium, all waves in that medium will move with the same speed. The difference then is that waves that have a longer wavelength will then be moving with a smaller frequency, and the other way around, because they all must comply with the fact that b is the same for all of them, right?
Yeah.
So basically, like in a rope, if we know that the speed, if we have a rope with such tension and mass, so that the speed in that rope is 100 meters per second, this is true for all waves that you send through that rope, which means then that if one wave, we send one wave with a wavelength of 20 meters, then its frequency will be 5 hertz. If we send another wave with much longer wavelength, so 100, so the crests are 100 meters apart, then the frequency is a lot slower, right? Because this wave is moving at the same speed as the red wave, which means that the crests take longer to pass, and you find that the frequency is 1 hertz.
Sir,
Yes.
I have a question about like the tests, like how they'll be made. Are the questions going to come like from the book, from Survey's like physics for scientists and engineers, or are they going to be like your questions or questions you found from other sources?
Well, I can't give away my secrets. No, I can. So I'll say this. The questions will be similar in format to the questions so the type of questions you can practice with will be similar to the types of questions asked on the test. So the type of stuff that you can do on the back of the chapter survey questions, and the stuff that I'll send you for practice questions before the midterms, it's a kind of stuff that you can expect to be asked in your tests, but obviously, little bit questions you haven't seen exactly before.
Okay. All right. Thank you.
No worries. So right, like so the idea is to practice enough questions that you get comfortable with the general strategy and approach, so that any new question that you haven't seen before, you can kind of apply the previous knowledge. For the last bit of this tutorial, though, I do want to talk about the wave function a bit. So the general approach when you're given a wave function is to kind of identify all the components of it. So this question is just asking you for all of that. Doesn't ask for the amplitude, but if I were to ask that, then you just point to the number outside the sine function, that's your amplitude. Now, if I go part by part, what is the frequency? So I just got to remember, right, that the frequency that's related to cycles, to time. So we always look at the term time for frequency, and we're talking about wavelength, right? We always look at the x term because that has a wave number. And the only annoying thing though is that when you give me the wave formula, right, like here, the numbers next to x and t are the wave number and the angular frequency. So we need to do some quick calculations to get the lambda and frequency as normal. But it's not too bad, right? Because we know from the formula right away, we're told the angular frequency is 400. So to get the regular frequency, we just divide that by 2 pi. So we get 200 divided by pi hertz. And honestly, you can leave this as pi, because if you plug it into a calculator, it's just a much uglier number. And just kind of following through here, we know the wave number. It's a term, it's a constant next to the x, which is in this case 30. And that tells you something about lambda, because lambda is equal to 2 pi over the wave number. And that's just always going to be true, right? For all wave functions like this. So you can then figure out that the wavelength is pi, 2 pi over 30, which is pi over 15 meters. And C asks for wave speed, which again is always the same thing. Here's a fun fact though. Using the relationship between f and omega and lambda and k, you can end up writing the wave speed in terms of omega and k. So you don't even have to calculate f and lambda. You can just take these two terms, divide one by the other to get the wave speed. Right? You can just do 400 over 30, which would get you 40 over 3 meters per second. And if you try doing lambda times f, you get the same answer, of course. And then for part D, what's the angular frequency? Well, again, that's the, by the way that the function's defined, it's always the term next to t, so we already know that. And then E wave number is 30. Okay. Okay, I'm going to show you on a graph. I'm going to graph this function and kind of talk about it. Talk about what the terms actually mean. So I'm just gonna jump into a new share. Quick tutorial screen, advance. Okay. Just trying to. So I got a graphing tool called Desmos, which is pretty cool. And what I got here is a graph of a function. So we basically have a sine function here. Can everyone see? Does everyone see like a red sine curve?
Yes.
Yeah.
Nice. Okay. So this is a wave function here, right? So the term in front again that sets the amplitude, right? So you can see how as that gets bigger, then the wave gets taller. So 1, 2, 3, 4. Then the term here, again, kx. So k is the wave number. This takes into account the wavelength. As the wavelength gets bigger, this term actually, the k gets smaller, which actually makes the function stretch out. So it actually accounts for the fact that a longer wavelength gives you a longer wave. So what I do have here, I have a parameter L for lambda. This changes the wavelength. So if I increase this, you see the wave gets longer or shorter if I decrease it. I also have a parameter here for my frequency, my angular frequency omega. But again, it's inversely proportional to the wavelength because we know that the speed is constant. So the speed is always equal to 6.8, 6.2 in this case. So as my wavelength gets bigger, the frequency must get smaller. And that makes sense because if you look at it like this, as I make the wavelength much bigger, the crests are now really far apart. but the wave's still moving at the same speed. So it's moving at the same rate, and it takes longer for crests to pass. Now, what if I make the wavelength smaller, then the crests are a lot closer together? Now I'm going to do this. I'm going to increase the time. So that means the time is moving forwards. And you'll see that as time moves forwards, you see the wave moving to the right. So note, like, over the course of about 10 seconds, about 2 crests have passed through. Right? We see 2 crests kind of pass through the y-axis. Now, if we make the wavelength a lot longer, though, and we start the time and go over 10 seconds, not a single crest has passed. That makes sense because, yeah, our wavelength is longer, so we're going to have a shorter, wavelength is longer, so it takes longer for crests to arrive. And note that overall, the wave is still moving at the same speed, right? Still moving to the right at the same speed of 6 meters per second. Even if I make the wavelength super long, the speed's still the same. If I make my wavelength super short, like this, the speed is still the same. The only thing that changes is now there's a higher frequency because more crests pass any given point at any given time. Also, we could just write, rather than writing k, we could write 2 times pi and then divided by lambda. And you can see, right, like the longer the wavelength is, if I make this 4 or 5, obviously that's going to make the whole graph bigger. It's the same thing with the angular frequency, right? The angular frequency compresses the graph, which makes sense. This is a angular frequency of 10. If we make it 20, everything's going to be a lot closer together. Except that actually, you can't see that in this case because the x is the variable. But if you were to make t the variable, then you see that increasing double omega also increases the frequency. And last thing is the phase shift I wanted to talk about, which again, the phase shift phi is just there to add initial conditions. So normally if it's 0, then it's doing nothing. If you make it 2 or 4, you see how it shifts function, shifts the origin essentially. And that's basically how each term affects the overall wave. That's the all time we have actually for the tutorial. We're gonna get kicked out in 10 minutes anyways, but does anyone have any questions about what we've done so far? I'm gonna send you a link to the calculator so if you can mess around with it. Okay. Yeah, how are we feeling? Do you have any questions about waves? Does the wave function make a bit more sense now?
Wait, the like phase shift like is read on the y-axis or the x-axis?
Sorry, could you repeat the question?
Like the phase shift like is read on the graph as on like the y-axis or the x-axis?
So the phase shift, both, because the phase shift essentially constitutes a horizontal shift along the x-axis. So, right, if I make that 0, if I increase that a little bit to say -1, right, the graph shifts to the right. So it shifts the entire function left or right. And therefore that affects both the values in the x and the y axis, right?
Yeah, okay. Thank you.
Okay, well, yeah, if no one has any more questions, then the tutorial is done. We're gonna do more of this in the next one, and also I'll send you. I'll make a recording too, talking about the power of a wave and the general wave formula. I'm not too worried about you fully understanding how the wave formula is derived. Just kind of like the general idea of what the formula is saying, more so than like the math of it. And the power is really just one more formula to know. If you know everything of the wave, then the power is just plugging in what you know really. And that would be it for chapter 16. Anyways, yeah, so have any more questions, feel free to go. Stick around for a few more minutes, but class is done.
Thank you. Bye.
No worries. See you Friday. Cool. Well, you too. Have a good day. Okay, I'm taking off. Zoom session will close automatically at 10. Again, if you have any questions, feel free to contact me by email. Office hours are at 7 on Mondays. And please read an email that the science director sent about a Science Help Center opening up soon. They will offer peer tutoring in the coming weeks. And that's all the announcements for today. See you next time. Ciao.